You all feel well, etc., etc. Sammy told me he's not very well. Hope he get better soon. We started last week to talk about the Cayley-Hamilton theorem. Want to remind you what it's all about. It's Algebra, of course. We know that for matrix A, of course, it is a squared matrix, n to n. Hi, how are you? And the polynomial calling px, choose an x to the power of n, and an minus 1, x to the power of n minus 1, blah, 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 a1x and a0. We have that the polynomial, when we put a in it, is an a instead of x, a instead of x, a instead of x. And the only difference is that we multiply the pre-coefficient with the identity matrix I. Now, Cayley-Hamilton's theorem. Cayley, that's our Cayley, right? It's weird. Cayley-Hamilton theorem states that PA of A is 0 for every matrix A in Fn to n, where PA is the characteristic polynomial of A. By definition, PA of X is the determinant of Xi minus A. Yeah. Looking at the characteristic polynomial that way, we actually have very something simple. I mean, if we put A instead of X, AI minus A, and we get the determinant of 0, which is 0, which is pretty logical as a proof to this theorem somehow. And one can discuss the way to prove it when we look at PA as an explicit polynomial. I mean, n, x to the power of n, etc., etc. We can discuss. But let's write it down in a different color, maybe. An explanation. And it's something quite easy. You talked about lime last lecture, no? Something bad. Let's have black. 17. Explanation. P of A. Why isn't it till as well? Oh, let's do it that way. P of A is the determinant of AI minus A. Which is A minus A, which is 0. Seems makes sense, right? But when we look at the characteristic polynomial explicitly, it's not that simple that easily shown that when we put A in it, we just get 0. And I want to show you an example what is Cayley-Hamilton is good for, and probably more exercises and more complicated exercise. Near will show you and practice. So, for example, I mean, we will use the Cayley-Hamilton, this theorem later on our course. But right now, we Cayley-Hamilton theorem gives us a way to write, for example, a minus 1 as an expression of a. That's in a simple example, all right? Which sometimes good. For example, look at numbers you like and five. Okay, go on. I'm listening. What? 3, 5, 4. Can have another 4 in Japanese. Lift the burden of deciding from your shoulders. All right, it's another 4. Now, the characteristic polynomial of A, easy to find, is just the xi minus a determinant in 2 on 2 matrix, which is not very difficult. Let's write it down explicitly in order to avoid mistakes. We have x minus 3, minus 5, 4, x minus 4, and it is x minus 3, x minus 4, minus 4, minus 5, which is x squared minus 7x and 12, 20 minus 8, as far as I can see. Yeah? Correct me if I'm wrong. Now we can go on. I don't want to do it, but here it's pretty easy to find the eigenvalue, etc. etc. We don't need to do this. Just a thought. And what do Cayley-Hamilton theorem states in this specific case? Now, by Cayley-Hamilton, what is the A? Hamilton. We know that P A of A is 0. But on the other hand, P of A, PA of A is just plugging A in instead of X, which gives us A squared minus 7A minus 8I. We enter matrix into a polynomial, we multiply the free coefficient with I, as we mentioned before. And what do we have here? Here, we can write down this equation as A squared minus 7A equals 8 times the identity matrix. And another step forward, we get that A multiplied by A minus 7I is I. And you know what? Let's just divide every side with 8. Now, by definition, going back to, I don't know, lecture number 3, maybe 4, on the first course, we know that if we multiply matrices and we get the identity matrix, these matrices are the inverse of each other. Meaning, I was right here. So, A minus 1 is 18. 18. 1 above 8 A minus 7I. Of course, we can check this out in this specific case. And oh, how surprisingly, it is true. But it's no, it's always true. And just remember, finding the matrix A minus 1, the inverse one is, of course, a technical process, but sometimes an exhausting one. I mean, using the row elimination, and we need to do it canonically, meaning we have to get to the identity matrix. And here we have a different way. I'm not saying it's take more or less time, but a different way to find the inverse matrix. And moreover, we can go on with this point. We can say that, hey, if the free coefficient is 0, for example, let's say we did not have this minus 8 here. We did have this minus 8 I here. We know that A is, what do I call in Hebrew? מחלקת אפס. In English, when the multiplication is 0, but none of the matrices is 0. Did errors define it in the last course? You zero combination or zero for linear independence, right? No. I mean when A and B, let's say, for example, A multiplied by B is 0, but not A nor B, none of them is 0. There's a name for that. In Hebrew, it's called מחלק אפס. Let's check out how do you call it in English. Right away. Wikipedia. Hope it's trustworthy. Okay, it's called zero divisor, which is literally מחלק אפס. If we did not have this 8, we get a squared minus 7a is 0. We know automatically that when a matrix is a zero divisor, it cannot be invertible. It doesn't have an inverse. Let's Control Z this back to the original. So we can use Cayley-Hamilton theorem in order to claim, let's be honest, some simple claims about the matrix and its inverse and similar things. When we, as I mentioned, we will use it later on in the further discussion when we talk about the next, not the next subject, the subject after the next subject, the day after tomorrow. Okay, so that was Kayla Hamilton. That was me. Any question about that? Okay, so I want to move on to a different subject. Of course, it's linear algebra, matrices, of course, but something that is not on first look connected to Cayley Hamilton, using the notion I'll define right now. One can prove Cayley Hamilton, but without using the determinant and putting an A, but running it explicitly, etc., etc. I don't think I'm going to do it. So, at the last homework, we wrote it down for that biodynamics. Cayley Hamilton. Yeah. Yes. So as I said, here we have an explanation, which seems extremely easy, right? Putting A instead of I and X, and then you get the determinant of 0, which is 0. But but it's not good. Yeah, it's not a simple question. What is missing here? What is not good enough in this explanation for it to be a proof? Yeah, but you don't have usually the time to prove anything we want to say, so I leave the proof maybe after that again. We'll talk about our next subject right away. Then we can prove the Cayley-Hamilton more rigorously. I don't know how to say it, but it's not extremely important to me. The theorem, though, we are going to use it. So what is our next mysterious subject is what called the adjoint matrix. Oh, right. Adjoint, one can call it actually adjugate, not the joint. The real, I call it a joint because it is joint to the matrix, but it's the right name is adjugate. Hey, it has a lot of names in Hebrew. מטריצה צמודה, מטריצה נלווית. It's like companion, but not companion. It's companion something else. But adjugate. In English, I don't have this problem, what to call it. So I want to define the adjugate matrix. I want to give you an example. I want to state the main theorem about it. I want to prove the main theorem. I think I want to do it. Let's roll with it. See? And after that, we will let's see the time and we'll prove the tiny Hamilton without. Okay, so what is the adjugate matrix? Let, it was good to have let A be a matrix order n. The bold, because it's a definition, adjugate matrix of A is denoted okay, adj of A and is defined as follows. Element by element. We let's see if he knows edge. Do you know edge? No, he doesn't. So I'll make you know it. The ij element of the adjoint adjugate. Adjoint is my I always call it adjoint, I don't know why. Of the adjugate matrix of A is minus 1 to the power of I plus j multiplied by the determinant of the ji minor of A. Let's remind you when mji is the n minus 1 over n minus 1 matrix, we get from A by deleting, that's what deleting is this, the j row and the I column of, it's probably the j, the rows, I something like that. But you understand that as well. Okay, so element by element, we can calculate the adjugate matrix. Let's write down an example. A 2 and 2 example will be too short. 3 of 3 probably too long, but I prefer the 2 and 3 example. And then we can say, okay, what do we do with this nice little adjugate matrix? For example, we look at, we can have our classic 1 to 9 matrix. Will be the same. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is A. By definition, this will be a bit exhausting, more than a bit boring, but one example is necessary. Okay, the 1, 1 element is minus 1 to the power of 2, and the minor 1, 1, which is the minor 5, 6, 8, 9, deleting the first row and the first column. And here we have 45 minus 48, which is minus 3. I got it right. You know what? So the PDF won't be that long. Let's write it down as a part of 9-row matrix because we need to calculate 9 elements. It's not mathematical point, it's just a style, which is the PDF shorter. What?
Again, what's the definition?
We define it per element. The ij element of The adjugate matrix is minus 1 to the power of I plus j multiplied by the minor, the ji minor. It's the switching the indexes. Now, after the example, we can say, okay, what is it good for? Okay, what about breakfast Stephens? What about 1, 2, 1 plus 2, and 1, 2. It's 2, 1, yeah. Ready to switch the indexes. Delete the second row, delete the first column, and you have 2, 3, and 8, 9, which is 6, 18. No, it is, yes, it is 6 because it's minus of the determinant. The determinant is minus 6, minus minus is plus. Know that, know that. And for Adjugate 1, 3, we have 1 plus 3, the minor 3, 1, deleting the third row and the first column. It is again positive, or at least the first sign is positive. And we have 2, 3, and 5, 6, which gives us minus 3 again. Okay, moving on. As I mentioned, boring, yes. Difficult, probably no. The element 2, 1 of the adjugate matrix is minus 1 to the power of 2 plus 1, multiplied by the 1, 2 minor. Yet again, we switch the indexes. It is minus, and deleting the first row, deleting the second column, we have, what do we have? 4, 6, 7, 9. This is using this minus is yet again 6. Okay, 4 out of 9. When we finish the next one, we've already done more than 50% of our work. So, aggregate 2, 2 is minus 1, 2 plus 2, we know 2, 2, 2. And first of all, it's plus. Secondly, deleting the second row and the second column leaves us with 1, 3, 7, 9, which is, as far as I can tell, minus 12, right? If I'm wrong, please correct me. Here, the last element on the second row, the adjugate 2, 3, minus 1, 2, 2, 3, the minor 3, 2, and deleting the third row. And the second column leaves us with 1, 3, 4, 6. And of course, a nice little minus at the end, which is 6. Okay, stay strong. We're almost there. The 3, 1 element is the determinant of the 1, 3 minor. The 1, 3 minor, deleting the first row. And the third column leaves us with 4, 5, 7, 8. 4, 5, 7, 8. Which is 32 minus 35 is minus 3. Moving on to the 3, 2 element of the aggregate matrix. 2 plus 3, the 2, 3 minor. First of all, it's minus. Secondly, deleting the second row. And the third column leaves us with 1, 2, 7, 8. Yeah, we will see our main theorem after the example, then we can understand it. Now it is 6 all over again. And last but not least, our 3, 3 element of the adjugate matrix, minus 1 to the power of 3 plus 3, the E3 minor, deleting the third column, the third row, we are left with 1, 2, 4, 5, which is minus 3. So in conclusion, the matrix itself was this nice little 1 to 9. And the numbers we got here were -3, 6, -3, -6, right? No, 6, -12, 6. And all over again, -3, 6, and -3. Okay. Any question about the adjugate matrix? So the main question is, what do we do with the adjugate matrix? This is our main theorem. What can we say? Do whatever about the adjugate matrix of A. Main theorem is the following one. For every A of order n, we have multiplying the matrix and its adjugate matrix, whatever way you choose to do so. First of all, we can stop here. It is not trivial. The two matrices commutative, change the order of in the multiplication, but it's not the main theorem. The main theorem states that when you multiply A with our adjugate matrix, you get the determinant of A multiplied by I. So the diagonal matrix, where every element of the diagonal is the determinant of A. So specifically, if A if the determinant of A is not 0, we know that A is invertible. We talked about in the first lecture. And we have just like the example of Kelly Hamilton we just did, we can divide both sides with the determinant of A, and the multiplication is I. When the multiplication is I, we just found the inverse matrix. We have that A minus 1 is the adjugate matrix of A multiplied by, or more precisely divided by, the determinant of A. And if A is not invertible, on the other side, on the other hand, when A is not invertible, we have that the multiplication of A and the adjugate matrix of A is just 0, because when A is not invertible, called singular, yeah, the determinant is just 0, and you get 0 all the way up. That's what happens in our example. We know that this matrix is not invertible, And one can check that multiplying A and adjugate A gives us 0. Um, Now, I want to prove the main theorem, yes, that the multiplication of A and the adjugate matrix gives us 0. But now, in order to prove it, we have two sides here, right? The adjugate with A and A with the adjugate. And while is invertible, one side is enough to uh, conclude that the other side works as well. When A is not invertible, it's not so simple. I mean, when you have two matrices, it's a proposition from first course. When you have A multiplied by B is I. Only one, just one-sided equation. You can derive from that BA is I as well. One multiplication gives us the other one. But when A multiplied by B, and here B is the adjugate matrix, when A multiplied by B is 0, it does not necessarily means that B multiplied by A is 0. And my theorem talks about both cases, when A is invertible and when A is not. So, in order to generally know that both of the multiplication, A adjoint, A adjugate, and adjugate A are both determinant of A multiplied by the identity matrix, in both cases, when A is invertible, when A is not invertible, when A is singular, I need the following lemma or claim or whatever. Before that, any questions about our theorem?
Um, I feel like what we did until now is a lot of like very technical and a lot of explanation, but I'm not sure like I can miss something.
I mean, first we started with definition and then very technical example, calculating 9 elements of the matrix. But then, as we studied the following theorem, what can we do with the adjugate matrix? In the bottom line, we can find the inverse, and that's, maybe I'll elaborate. That's an important, um, a significant equation. Till now, how do we, when we needed to, how did we find the inverse matrix? Using elimination, using row operations. Now, with all due respect to row operations, which can be stated, phrase, whatever, algorithmically, do A, B, C, D, E, F, G, and then you'll get your canonical form of A, which means you get your inverse A minus 1. It's still many times, many occasions when we are, as human beings, finding the inverse matrix, we do it not so algorithmically. We say, oh, that element is 5. It's possible, but not very convenient or nice to use 5 in order to eliminate all the elements beneath it. I mean, if you have 5 and 2, so let's R2 minus 2 above 5 R1, fractions, not nice. Maybe we divide all the first row with 5, something like that. And these thoughts cannot always be phrased as something purely algorithm. I mean, asking the computer to do so. No, computer, when the element is a bit complicated, why don't you change the rows? Eh, what is a bit complicated? It's not something you can define pretty easily. Now, we have a way to find our inverse matrix using only determinants, only multiplications and sums of the elements of the matrix. I mean, this is determinant, right? And the adjugate matrix is calculated using determinants. So right now we have a um, very, very strong word, yeah, but an important and significant formula calculating the inverse matrix without using a single row operation. It's easier to ask the computer to do this from our perspective, yes, from our point of view, writing the code to do that, yeah, or asking GPT to give us the code to do that. No, no, not kidding, man. If it's the code is complicated, the probability of GPT making mistakes, you know that better than me, gets pretty close to one, right? Pretty high. So it's important that we can use only determinants to find the inverse matrix, and finding the inverse matrix as a problem, as the problem itself is of course very basic and important if we thinking, as we mentioned before, of multiplying with A as some, changing the character, the player's character uh, status, move one step forward, one step backward, lift your weapon up or something. Then, in order to find out who we came from, multiplying by a minus one is the common, is the right thing to do. So, this was my short elaboration about why this is important. But as I mentioned, and it's probably important in my proof, uh, it's not the whole picture. Means the theorem is correct not just for invertible matrix, but for singular matrices as well. So, in order to prove the main theorem, we need the following proposition. So, proposition, title, underline, etc., etc. Proposition. Let A be a matrix of order n on n. So the adjugate matrix is defined. Then the adjugate matrix of the transposed matrix of A is the transpose of the adjugate matrix. Let's write it down. Be more understandable. When the transpose is inside or outside, it's the same. Here, on the left side of the equation, at first we calculate the transpose, then calculate the adjugate matrix of the transpose. The other side, we first calculate the adjugate matrix of A, and then we do the transpose. Okay, let's prove the proposition and use it to prove the main theorem. We discuss an equation, equality equation, whatever, between matrices. So we know we have to work per element. What we actually need to prove, we need to show that the ij element of the aggregate matrix of the transpose matrix of A and the ij element of the transpose of the aggregate matrix of A are the same for every I and j. But by the definition of the transpose on one hand and definition of the adjugate matrix on the other hand, it shouldn't be very hard. Okay, so let's write down explicitly both of them what they actually are, and we'll find out very surprisingly that they are the same. So the ij, or let's start with that. The ij element of the adjugate matrix of A is actually, by definition of transpose, the ji element of the matrix itself. Now, by the definition of the adjugate matrix, we have here minus 1 to the power of j plus I multiplied by the ij minor. Yet again, when we talk about the adjugate matrix, we switch the indexes. The ij minor of A. On the other hand, when we look at the ij element of the adjugate matrix of A transpose, we have by definition -1 to the power of I plus j multiplied by the determinant of the ij minor, by the ij minor of who? The ij minor of A transpose. Let's put, so it's, yeah, it's the ji minor of A, and it's, they're both same. And one can explain, I mean, when is the minor of A transpose, which by the definition of transpose, switching the indexes, it's the ji, it's my, I'm wrong, ji minor of A. So they are basically the same by the definitions of transpose on one hand and the adjugate matrix on the other hand. Um, you know what? Let's add another step here in the proof because it's use another step. It's not shown. The how do I want to say it? I mean, no, on the one hand, I think it's enough. I mean, if I write it down explicitly, that's what bothering me. Let's add A to say that explicitly that it's the minor of A. Okay. So right now, instead of this T, we can say, hey, that it's the minor of A T, right? Which is the transpose of the minor of A. Um, yeah. And right now, it's not the same minor. It's the ij and the ji. But why? It's still the same element, because we don't talk about the minors themselves, we talk about the determinants of the minor. And one of the properties of determinant we discussed here earlier in our course is the determinant of the transpose is just as the same as the determinant of the original matrix. Yeah? So I want to say something like that. The determinant of the ij minor here is the determinant of the transpose of the minor, and when it comes to determinant, we can just transpose, we can give up on our t, we can just put it down, the ij. It was already understandable at first, but I mean, there's another step at the background, using the fact that determinant do not care about transpose.
I mean, the
I
part
mean,
that
I want to, yet again, be more precise. It's the ji, which is the minor of the ji, whatever. And here it's just the same. Because the determinant doesn't care about transpose. That's my point here.
is confusing about or I think that you know that the same the transpose of the minor is on the same sign. And I don't know if I understand what I mean.
Not quite, because it's the sign is I plus j, j plus I, it's the same. The sign is determined by the sum of I and j. So it's ji or ij, it's still the same. It's I plus j. As far as I understood your question.
Yeah. It's just interesting. I play the same, yeah. but the
Yeah.
minor, it should get AI or it.
Now, I mean, by definition of the adjugate matrix, we switch the indexes. So if it's the the ji element of the adjugate, we use the ij minor. Now, when it's the ij element of the adjugate matrix, we use the ji minor. And now for my point, the minor of the ji matrix, the ji minor of A transpose, is the ij minor of A, just transposed. And using the property of determinant, we can send the transpose away. It's the same determinant. Any other questions? So now, how do we use this proposition to prove our main theorem? We want to show that the determinant A multiplied by the adjugate matrix is determinant of A multiplied by I. Okay. So firstly, we show that A multiplied by the adjugate matrix is the determinant of A multiplied by I. And then we will use our proposition to change the order of A and adjugate A to get the second equation. Okay. So yet again, what we need to prove is equation matrices. We need to show that for every I and j, the equation holds. We have the same elements. So we need to show that the ij element of A multiplied by the adjugate matrix is the ij element of the determinant of A multiplied by I. We know what are the elements of the matrix on the right hand of the equation. We know that if I is equals J, meaning the element is on the diagonal, it should be the determinant of A. And when I is not J, the element should be 0. We have two cases. If I is J, that's what we need to prove, right? Then the element is the determinant of A. And if I is not J, then the element is just 0. So these are the elements. Oh no, I missed it. So that was like that way. Then the element is 0. Oh, yes, in one line. Okay. Both cases have practically the same proof, but let's write it down explicitly. Okay. If I is not J, by definition, so by definition of matrices multiplication, the ij element of the multiplication is the sum, let's use the letter k, k goes from 1 to n, of the ik element of the left matrix and the kj element of the right matrix. And that's the definition of matrix multiplication. You see, so with errors, probably it was extremely fun. Now, we know by definition what is the element of the adjugate matrix, the Kj. By definition, it means 1 to the power of k plus j multiplied by the determinant of the jk minor, right? So now using definition of matrix multiplication, using the definition of the adjugate matrix. If I is j, we have that element let's say instead of I write j or instead of j I write I, it's the same. It's the sum, k runs from 1 to n, aik minus 1 to the power of k plus I, determined multiplied by the ik minor. One can change, not necessary, but probably easier to look at it. One can change the order of the elements in the multiplication. And what do we have here? It's our nice formula with using the permutations, but it's a nice formula for determinant. It's not a definition. It's a definition is with using permutations. It's a formula we've already seen. I don't think it's lecture number 1 or just in lecture number 2, but that's the formula of the determinant. The element multiplied by the minor multiplied by minus 1 to the power of k plus I. So it's as required when I is j, we just get the determinant of A. Now, as I mentioned, it's a similar proof, but it's a bit more interesting. What happens when we have I which is different than j? Yeah. Why do we have here a matrix with determinant 0? What happens when I is not j? So if I is not j, intuitively, what does this formula gives us? It gives us like the determinant of A, but instead of using the J row, we use the I row. Intuitively, it is a determinant of a matrix which have two same rows. The I row and the J row are the same. And a matrix with two same rows is not invertible and has a determinant 0. Now, formally speaking, we can define a matrix B or some different letter, a matrix B as the matrix which is the same as A. Matrix B by the R, let's say Rk of B is the R K of A for every the same row for every K which is not J, and for J the J row of B is the same as the I row of A. meaning that B is the same matrix as A, just that the J row is not the J row of A, but it's I row, meaning that B has B satisfies whatever satisfies Ri and Rj are the same. What do we get from this formal shenanigan? When we have our matrix B and we look at the ij element of A multiplied by adjugate matrix, now the rows of B are the same as the rows of A. Specifically, the I row of B and the I row of A are the same. So we have B instead of A. Moreover, when it comes to B, when you delete the J row, which is the only row that is different from A, when we delete the J row, we get the same exact minor as in A. I mean, the only difference between B and A is the J row. When you delete it, and that's what you do when you calculate the JK minor, you get the same n minus 1 on n minus 1 matrix from A and B. So while we think of this minor as a minor of A, we can actually think of it as a minor of B as well, because they are the same when you delete the J row. Let's write it down explicitly. Note that when we delete the J row, A and B are the same. So the JK minor of A, not minor of A, equals the JK minor of B. And right now, logic explicitly is right down in the proof of the proposition. This is the JK minor of A, but it is the same as the JK minor of B. Yet again, intuitively, here we have the formula for determinant, but using one row, I row, for the elements, and second row, the J row, for the determinants of the minors. Now, formal and determinant of a matrix with two same rows, I and J, so probably zero, but formally speaking, we use actually this kind of matrix that is A all along the way, besides the J row, which is the same as I. And now, when we talk about B, we have the determinant of B by the formula of determinant. And because B is a matrix with Ri and Rj are the same, then its determinant is zero. Let's go with this line. B is not invertible, and so the determinant of B is zero. So by the end of our first part of the proof, it doesn't matter which element we look at, I is J, I is not J, we get the same. When I is J, it's the determinant of A, and when I is not J, is the determinant of a matrix with two same rows, which is zero, as we wanted to prove. Now, it's not the end of our proof because we talk about the second equation where we multiply edge and a, not a and edge. But using a proposition, it will be not very hard, as you'll see right now. Before that, any questions about what we've already um, achieved in our proof?
So, we can go
Yeah. More?
out. No. So there's a single row that we define as J here or K, where instead of putting what's in A, we put the result of the minor function.
Yeah.
Because the calculation we take out one row
And one column. After you delete this one row, you get the same matrix.
yeah.
So you can think of the JK minor of A as the same as JK minor. Well, you can write down, and annotate an example. Let's say we have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And on the other hand, we have a matrix 1, 2, 3, 0, 1, 1, 7, 8, 9. Now, calculating every minor from the form M2K, where we delete the second row, we will have the same minor in both of the matrices. That's my point.
Yeah. But you would, the values you put in that row are important, right? Because regularly, but you multiply it by the minority of the determinant.
Yeah, but because we talk about a matrix where we put in the second row a different one, let's say it's 1, 2, 3 all over again, we know that the determinant will be 0 because it's non-invertible matrix.
Okay.
Any other questions? Okay, let's delete the drawing and continue with our next step of the proof. Now, we need to show that the adjugate matrix multiplied by A is determinant of A multiplied by I as well. We already know that it goes the other way around, what we just proved, using many fixed and tricks and determinants. And what happened when we transpose both sides of the equation? We have A multiplied by the adjugate matrix, all match transpose. And on the other hand, determinant of A multiplied by I, all that transpose. Now, we know transpose for a long time, last year. You study of the summer? You had the summer semester or no? Oh, wait, it's your second one. On one hand, when we transpose a multiplication, we transpose every matrix and change the order in the multiplication. So we have the transpose of the adjugate multiplied by the transpose of A. And on the other hand, when we transpose a matrix multiplied by a scalar, the scalar isn't changed, and we transpose the matrix itself. And right now, what can we say about both of our sides? On one side, the transpose of I is just I, right? And on the other hand, the adjugate matrix of the transpose is it's the transpose of the adjugate matrix is the adjugate of the transpose. So I transpose is I, and by our proposition, we have that the adjugate exposed is the transpose adjugated. So our equation becomes the adjugate of the transpose multiplied by the transpose. And you know what? Let's take a step forward. Instead of the determinant of A, we have the determinant of A transpose multiplied by I. And it's the same as what we wanted to prove. It's just written with A transpose and not with A. So one can start this equation using A transpose and not A in order to get the final equation with A itself. Or one can say that, you know what, we plug in B instead of A transpose and just get what we wanted, whatever, however you want to do it. Let's start with the A transpose. It's a bit more elegant for every matrix. So now I just put transpose all over the place, transposing the hell out of it. So it transpose with two transposes, which is zero, and a transpose. And presently we have the adjoint of a transpose. So we have transpose. Now transpose are just canceling each other. See, well, so we got what we want. Write it down explicitly. Determinant of I transpose, the I transpose itself is just I. The determinant of A transpose is determinant of A, and blah, blah, blah. So when we start with what we already know, but using it on A transpose, and then we transpose both sides of the equation, we get what we want. And again, we can do it on A itself, and then at the end of the proof, claim that it is true for every matrix, including A transpose. This is the second side of the theorem, and QED, we got what we wanted. The multiplication of A and N transpose from here, from there, from everywhere, gives us the diagonal matrix. It's even more than just diagonal matrix. I don't know if you ever encountered the name. I don't think I mentioned it here. Probably maybe errors. When the diagonal matrix has the same element all over the diagonal, we call it a scalar matrix. Scalar, because just scalar multiplied by I. Okay. Um, any questions about the proof? Okay. So I just want to define, as yet again, we can use the adjugate matrix in order to prove the Cayley-Hamilton, not just by the explanation we explained before, but rigorous, nice formal proof. We did here a nice rigorous formal proof, so as we can pass and move on to our next subject, we'll use Cayley-Hamilton in this subject as well, as we will see probably after the break, but we'll see it shortly. So our next subject is what I call the minimal polynomial. Let A be a matrix in F and on N. The minimal polynomial is the polynomial with minimal degree, and what I call a monic polynomial. I mean, the coefficient of the highest power is 1. I'll write down shortly. That gives us 0 when we put a in a. Let's write down explicitly. The bold because definition minimal polynomial of a is denoted ma of x or whatever variable you like. It is the monic polynomial with monic the coefficient, yeah, that's right, coefficient of the highest power is 1, just like the characteristic polynomial, which is always x to the power of n, and then the coefficients start to get nasty. Is the monic polynomial with the minimal degree that satisfies putting a in it, and you get 0. Now in Hebrew, you say as a verb, me'apes. How do you say it in English? Zeroing? Don't think so. Zeroing? Okay. Zeroing works? Okay. The minimal polynomial that's zeroing a. And yet again, because one can think of, okay, if it's x minus 2, it's probably 2x minus 4. So in order for it to be unique, we define it as the monic polynomial with the coefficient of 1 for the highest power. Let's write down a quick example, and then we can take our break for a simple example. Simple example. Let A be I. The polynomial fx x minus 1 satisfies when you plug a in it, you get 0. It's I minus I. And is monic, semicolon, because it has degree 1, it's also the minimal degree. Yes, it is the minimal degree of a polynomial that satisfies if a is 0. So conclusion, the minimal polynomial, the one with the minimal degree that zeroing a is x minus 1. Now we'll talk about the connection, or probably connections, between the minimal polynomial and the characteristic polynomial. We can have nicer, more complicated examples. This will be our next subject. Probably, I think we'll finish what I want to say about it in this lecture and start our next subject next lecture. But let's roll on and see what we get. Okay. Any questions before we go on a break? Whatever. You should remember that the break is always 15 minutes bunker. You say it. Netto. Okay, so let's have our break. Let's stop the recording. It's your duty when we start it again to say a lot. Resume recording. And okay, I'm here as well. So we continue to discuss the notion of a minimal polynomial. First of all, I want to give you one simple but simple and effective. We need to say that explicitly every matrix does have a minimal polynomial. It's something that always exists. Um, so a proposition, claim, whatever. That's going to be Hebrew. Proposition. Every matrix has a minimal polynomial. Proof or an explanation, like um, we know that let A be a matrix, okay? More formally, what? Yeah, you know, did. And, so we show something you whisper to the actors. Um, let A be a matrix. We know that by Cayley Hamilton, there is a polynomial that's zeroing A, or A is zeroing the polynomial, it's the same. This is zero by Cayley Hamilton. So they're always a polynomial that's zeroing, let's say it's zeros. It's a verb, it's weird. A. Now, if moreover, we know that the degree of PA is the same as the order of the matrix is n, as we mentioned before. Now, and even more, PA is a monic polynomial. Know that PA is determinant of xi minus a. So we've already seen, not once, not twice, this determinant gives us x on the diagonal, which ends up with x to the power of n. So the coefficient of x to the power of n is 1, meaning that the polynomial is monic. And now, we do have a monic polynomial that zeros a. And now, if there is not, there is no polynomial with degree less than n that zeros a, then PA is the minimal polynomial. There's no one with a smaller degree. Now, if there is the other end, if there is a such polynomial, let's call him, I don't know, f, then we can look at f and consider the same consideration. If there is no polynomial with a degree less than the degree of f that zeros a, then f is the minimal polynomial. And there's such no monic, yeah, no monic. The one here. And if there is a polynomial, monic polynomial that zeros a with a degree less than the degree of f, let's look at this polynomial, and so on and so on. So we look at f and do the same. Because n is a finite number, somewhere along the way, we will stop. Okay, this is the polynomial, and there is no such polynomial with a degree less than our degree. Monic polynomial, that zeros a. Because n is finite, we will eventually stop at the polynomial. The monic polynomial, let's call him, g. Yeah. The coefficient of the highest power is 1. For example, x minus 1 and not 2x minus 1. Instead of 2x minus 1, we'll think of x minus half, something. We'll eventually stop at the monic polynomial g such that g is a, and for every polynomial and of edge with leg of h is less than leg of g, the h is not zero in a, so g is what we define as the minimal polynomial. Let's go on with the process till we finish. Any more questions about that?
I mean, this is like saying we select a random polynomial of degree less than n, and if we find one that the
Yes, I mean the process here is not something we use technically to find the minimal polynomial. In theoretically speaking, I say, okay, if there exists a polynomial with less degree, blah, 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 then we'll move forward with this polynomial. If not, then our polynomial right now is the minimal polynomial. And because we start with a finite degree n, and we, with every step, or stop and say this is minimal, or we move forward to a polynomial with a degree less than the current degree, eventually it will stop. We'll talk about how technically to find the minimal polynomial, but we're going to need some other propositions, theorems, in order to do so. Any other questions? Okay. Now, and it's probably similar proof, the minimal polynomial it doesn't just exist, it is also unique. I mean, the minimal polynomial of A is just 1. I mean, it's in the name, right? Minimal is this probably unique, but we should probably write down explicitly the minimal polynomial is unique. Now let's explain. What? Oh, yes. Explanation. Say that let f and g be both minimal polynomials of A, means that f has the minimal degree and g as well, because f is minimal, f the deg of f is smaller than the degree of g, and the degree of G is less than the degree of F because G is minimal. So they have the same degree. Moreover, we know that they are both more F and G are both monic. So we can write that line matrix for short as PDF. Fx is something with x to the power of, I know, some k, and then ak minus 1, x to the power of k minus 1, and so on and so on, a1x plus a0, and the same thing for g, but different right now. Different coefficients. We want to show that they are actually the same coefficient, ak minus y and bk y, ak minus 2 and ak minus 2. And we know that f and g being minimal polynomials, meaning that when we put a inside them, we get 0. So we have this with a, and this with a instead of x, I'll just write it down, are both 0. When they're both zeros, they're probably, they are the same. So ak instead of x, and every x I change to a on both sides of the equation. And we have this nice relation where we have here I and I. Now, we can move every element to the left side of the equation, for example. First of all, AK and AK cancel each other, and the 0, I just move all this stuff to the left side, and I have these elements minus these elements is 0. And of course, we can put them together in pairs. The coefficient of AK minus 1 is AK minus 1 minus BK minus 1, and so on for every other coefficient. The coefficient of A is A1 minus B1, and the free coefficient is A0 minus B0. Now I know that this equals 0. What does it actually say? It says that we have here, what do we get? What do we have here? What do we have here? Denoting, let's call it, I don't know, Q. Enough letters in the Latin alphabet. Qx be the polynomial of matrix we have here. X. And we know that, or nothing that we have QA is 0, right? What we got here? Plug A. And this polynomial, you get 0. Now, what is the degree of Q? If it is xk minus 1 or any other degree, if any one of the coefficients is non-zero, Q has a degree larger than 0. Yeah, let's write it down. Now, if AJ, I don't know, is not BJ, for some j between 0 and k minus 1, we have a polynomial of a degree less than k, because maximum k minus 1, that zeros a in contradiction to the fact that the degree of the minimal polynomial is k. Yet again, by definition, the degree of the minimal polynomial is the smallest degree of a polynomial that zeros a. So, don't want a contradiction, right? Aj is bj, or every j, and the polynomials f and the g are the same polynomial. They have the same coefficient. Fine. Happened to start actually became, can call it a proof or just an explanation. I'm going to start with two minimal polynomials using the minimal, the polynomials. You do have that they are basically the same. Yeah.
I don't think that the way it's wants the
We don't say the what use?
that the function QX is one, that's what it's meaning.
Yeah. But right now, if there is coefficient that is not zero, you can divide both sides with this coefficient and get a monic polynomial. So it's the same. Any other questions? Okay. So right now, for the it's not the main theorem about minimal polynomial, but it's the main theorem considering the technical way in order to find such a minimal polynomial. Okay. There's a proposition or a theorem, whatever. Let with a big L, capital L. A be a matrix of order n. And let, I don't know, F be a polynomial that zeros A, such that Fa is 0. Then the minimal polynomial of A divides F, meaning that F is the multiplication of the minimal polynomial and some other polynomial. We cannot have a polynomial zeroing A and not be divided by the minimal polynomial. We use the theorem, the process we mentioned before, the theorem of dividing polynomials with a remainder. Now, let's prove it. Let's prove it. First of all, be clear. If f is 0 and automatically it's zeroing a, then of course the minimal polynomial is dividing 0. Everything divides 0. Yeah, because What is the definition of dividing? MA divides F. It means that F is the multiplication of MA and another polynomial. Now, if F is 0, of course we can write F as a multiplication of MA and another polynomial of MA and it's just 0. So, by definition of dividing stuff, dividing thing, we know that is correct. Let's write it down because semicolon, everything divides 0. Now, what happens if F is not 0? We can divide F by MA, having that F of X, let's write it down explicitly, is let's sum QX multiplied by MAX plus RX when R is the remainder. And what do you know about dividing with the remainder? We know that the degree of the remainder is smaller than the degree of the polynomial we divided by, meaning that the degree of R is smaller than the degree of M. We want to show that that F is divided by MA, meaning that the remainder R is just 0. Yeah? We want to show that R is 0. One can assume a contradiction or maybe even without it, but let's do it that way. Assume in contradiction. What do you tell me how it's called? By contradiction. That Rx is not 0. And we have, if we put A inside the equation, we get FA is QA multiplied by MAA plus RA. Now, it's given to us that FA is 0. On the other hand, by definition, MA of A is 0 as well. No, skip right down. FA is 0. It's given to us. Was promised to us. MAA is 0. And so we end with 0 is RA. What do we have here? A polynomial with degree less than the degree of MA that zeros A. Contradiction with the definition of minimal polynomial. That is the polynomial of the minimal degree that zeros A. Definition of MA. So R must be 0, and when a polynomial is zeroing A, it must be divisible, yeah, that's the word, divisible by MA. Okay, any question about this proof? Those you write down. Have another couple of seconds. And then I want to move on. What? Hi, how are you? Want to sit down? It's an English lesson, yeah. You know what you're gonna do after the lesson? I'm gonna do Argazim, baby. Yeah. No, no McDonald's. No, no McDonald's. Bye, Monty. Yes, third year, something like that. Okay. I want to, first of all, a corollary. That's right. Call it right. Corollary. Um, we know that PA of A is zero. We call it the Cayley-Hamilton theorem. We said we're going to use it. Here we are using it. So by our last theorem, the minimal polynomial divides the characteristic polynomial. One can say that the minimal polynomial is minimal, but with a slightly different approach than definition. By definition, what is minimal? The degree of the polynomial, yeah? When we think about the order of natural numbers, the degree is a natural number, it is smaller than every other degree of a zeroing polynomial. But now we can think of the minimality of the polynomial and minimal thinking of the dividing and divisible by order. I mean, MA, what is the minimal element? Using the discrete mathematics definition. Yeah, we have some in Hebrew it's called Yahas Seder, order relation. What is the minimal element? But every other element relates to it. Yeah, A is minimal if A psic B is B is an element of the relation for every B. Now, if we think of dividing as an order relation, and it is one, every polynomial divides itself if f divides g and g divides f and f is equals g, etc., then MA is the minimal element of the set of the polynomials that zeros A in that notion. Minimal in the dividing or divisible by relation. Specifically, it divides, generally speaking, it divides every polynomial that zeroing f, as we've already proved, and specifically, it divides the minimal polynomial. Now, for another, probably our last claim about the minimal polynomial itself, then we're going to start to see where we're going to use it. Another proposition.
Sorry.
Yeah.
The polynomial of A
Is zero.
yeah, and
Also possible.
possible.
Yes. Correct. Okay, another proposition. We're not going to prove it now. Proposition, but you trust me, bro. If f a is zero, let's write more precisely. Let's f now f a be some matrix in order n, of order n. And let f be a polynomial such that f a zero. Just a reminder, we know that we can denote the set of all polynomials with coefficients in field f to be fx, right? We know this notation. With polynomials such that f a zero, then if you take the polynomial f and take it to the power of n, the order of the matrix, what you get is always divisible by the characteristic polynomial. And specifically, that's right, with double L. Specifically, if you take the minimal polynomial and you look at the nth power of it, where n is the order of the matrix again, then it is divisible by the characteristic polynomial. Now, why is that true? As I said, I'm not going to prove today, maybe later on, maybe not. We can't prove everything we say. We can, but end up with 3 lectures, something like that. What I want to say is that from here we get an important, we'll see why it's important in our next subject, probably most of it in next lecture. Just בעזרת השם, שנהיה בריאים וכולי. Every component, every element of the characteristic polynomial PA that we know that is corresponding to an eigenvalue, etc., appears in the minimal polynomial because it is divided by the minimal polynomial. I mean, we cannot have x minus 2 in MA and not in PA, right? Because MA divides PA. But from this proposition, we can say that is also correct vice versa. Every element of the characteristic polynomial appears in the minimal polynomial. So we can write it down as a corollary as well.
For every constant in
It's not functions, just polynomials. Yeah.
Polynomial in f the infinite polynomials or fxn?
No, it's without any limitation of degree. Every polynomial for itself is finite by the terms of how many components we are summing. Every polynomial has a finite degree, but we do not limit ourselves here. Okay, because MA divides PA, every component, I will say it, irreducible component of MA is an irreducible component of PA. On the other hand, capital, write it that way. The polynomials MA and MA to the power of n has the same irreducible components, just different powers. So PA divides MA to the power of n gives us that every irreducible component of PA is an irreducible component of MA. So in the bottom line, PA and MA has the same irreducible components, have the same irreducible components, and the only difference is maybe in the powers them. The powers of these components can be smaller when you talk about MA. So now, for example, Um, let a matrix of order 3 of 3 be a matrix with a or with PA is two numbers you like.
Uh,
Okay. What can be the minimal polynomial of such A? By our last corollary, the same irreducible components of A appear in MA. The only possible difference is in the power of every reducible component. But we know that the power of every reducible component in MA is smaller or equals the power of the same component in PA. So, in conclusion, for MA, we have two options. In such case, MA can be the characteristic polynomial itself, or x minus 6, x minus 9. Yet again, that's because the that's because the irreducible components. Oh, here, irreducible components x minus 6, x minus 9 both have to appear in MA as well. And on the other hand, no other components can appear. Either semicolon, and moreover, the power of every component MA is smaller or equal to power in PA. So only two options. So now, technically speaking, when we have a specific matrix in front of us, and we want to calculate the minimal polynomial, we firstly calculate the characteristic polynomial, determinant of xi minus a, etc., etc. Then we can write down our options for the minimal polynomial using the same consideration as we did here. And then finally, when we have two options, specifically here, or maybe more when the matrix is larger, we have to check which option checks out by hand. Meaning, if I have a specific matrix A with such um, characteristic polynomial, these are the options for the minimal polynomial. If I want to decide which option is the minimal polynomial, I take the matrix A and plug it in one of the polynomials. Let's say I plug it in here. If it is 0, nicely done. It's the minimal one because it suffices everything a minimal polynomial should suffice. If it is not, then uh, it must be this one, because there are two options. This is not one. It's not the one. So when you have a specific matrix, one can, technically speaking about calculating the minimal polynomial in that way, finding the options for the minimal polynomial, using the characteristic one, and then it's called misui v'tiyah, and trying and maybe have some failures on the way. No, it's not such, no, it's not a formula like the characteristic polynomial. Like you plug in x I minus a, it will be long, will be tough, will be boring, will be whatever, but we get through it. The minimal polynomial is by definition the minimal degree, whatever, etc., etc. So using these propositions, corollaries, theorems, we we minimize the war episode, as I mentioned before, when we started with the, no, before the, when we came back from a break and we said, okay, every polynomial, the minimal polynomial, I'm sorry, the minimal polynomial exists, was yeah, if there are one polynomial with a degree less than its degree, blah, blah, blah. But how do we find this polynomial? So it was only theoretically speaking. Now, technically speaking, we can do it that way. Find the quadratic polynomial, having our options, probably be numerous, not so many options. And in order to find the exact correct one, we need to put a in the polynomials and see if they are zeroing a or not. Okay. Yeah.
Say that the MA is the combination of both, or in some cases it's only one of them. How?
No, it's always only one of them. It's unique. It's one polynomial.
Oh, yeah. Then the combination of the equation of the
Irreducible, yeah.
power of one.
Or to the power or here. But it cannot be, first of all, it cannot possess. It cannot have any other components, because you have to be the same components as the characteristic polynomial. And on the other hand, the power of every component cannot be greater than its power in the characteristic polynomial, because MA divides the characteristic polynomial, not vice versa. So we have components here, as they should appear, they must appear in MA. And here, because we have this power of 2, in the minimal polynomial, it can be not 2, but 1. So we have two options.
There are some fixed for the characteristic polynomial and power of.
Yes, yes, there are. Let's, you know what, let's write down examples and see how we use our last minutes. And the next subject is a big important one. And we, of course, we're going to use the minimal polynomial in talking about it, but more than that, probably it's for the better to start it freshly. Next lecture. This is lecture number 6, right? Yeah, okay. So now next week is gonna be the already half of the semester behind us, right? Time is running and we are enjoying. That's what you say, people. Now, for example, for a simple example, we'll see the example again probably next week. We look at the following matrix. Let it be, oh, let's do it. We have it's enough. Number you like? 3. All right. 3 and 3. The number 3. Everything is connected. 5, not now. No. I mean, I've already read one. Yeah. Thank you. No, I want it to be simple, okay? I want it to be simple. You know what? You can put a 5 here if you want. Whatever. Yes, whatever. You go with it. Now, here, it's a triangular matrix. The characteristic polynomial is easily found. It is x minus 3 to the power of 2 multiplied by x minus 5. Okay? You know what? Let's put 3. Nah, I don't want to be too long. Okay? To be 4 or 4, it's exhausting. But probably it's for the best. If it's a 4 or 4, will be more convincing. Okay, so that's 3 and 5. Yes, and zeros and 1. What? Um, I want it to be easy to calculate. I mean, when it's a triangular matrix, we can easily find the characteristic polynomial. It's just elements of the diagonal. No, it's not bad. It's fine. We can use 0 instead of x if you want. It's just 5. Now, what are the options for the minimal polynomial? X minus 3, x plus 5 must be there. The powers can be 2 or 1, not greater than 2. You cannot pass the characteristic polynomial. So we have 3 options for the characteristic polynomial. The minimal polynomial, it can be x minus 3, x minus 5. It can be x minus 3 to the power of 2 multiplied by x minus 5. Oh, sorry, it's 4. 4 options. Silly me. It can be x minus 3 and x minus 5 to the power of 2. And it can be x minus 3 to the power of 2 and x minus 5 to the power of 2. It can be the characteristic polynomial itself. Now, in the worst case, we have to check 3 options. And if 3 of them are not 0, then the fourth one will be our minimal polynomial. Minimal polynomial. Hopefully, we'll end it sooner. So let's try. Which one? Which way? See a student? Yes. We just put A. Let's try and see if A, x is A, gives us 0. Right now, there's not a better way. Maybe next week, the week after next week, we can talk about better ways. As far as I remember, no, we do miss one class. Next week is not Hanukkah yet, and in Hanukkah we do learn, but after Hanukkah we have a Sarah Tevet right now on schedule. It's fine. We have 13 lectures, and even though we miss one, it's after that, but probably talking next week. Next week. Okay, gives us 0. Let's put A here, and we'll be very disappointed because it is not going to be 0. Give us this, and okay, let's put it down. So 4 and 4 matrices, but most of them 0. Nice. And moreover, one element is not 0. The matrix is not 0, and don't have to calculate everything we do. Minus 3 I gives us this matrix, and minus 5 gives us this one. Now, if we multiply the matrices here, the element here, row and column, gives us minus 2, which is not 0. Whatever the element are, if don't think, let's write it down. Okay. The 1, 2 element is minus 2. So it is not 0. And x minus 3, x minus 5 is not MA. For the other option, now let's take the correct one. Right one. If we do it with x minus 3 squared, we have this matrix. This one is squared. Now it's a multiplication of three matrices, right? We multiply this matrix by itself, and may Allah forgive me. I'm a grown-up. All right. I have a PhD in mathematics. I'm a father of more than one child, etc., etc. Okay. My knees hurt, whatever. When it comes to matrix multiplication, I write them side by side and do this choreography with the finger in order to not be mistaken, okay? To not fail. Multiplied, forget my I multiplied, seriously, no jokingly, thousands of matrices throughout my career. Not only tens of thousands, but probably thousands. I mean, every practice, every lecture, every homework as a student, probably thousands already. Okay, multiplying that, let's finish nicely. It is 1, and it is 0, 0, 0, 0, 0, 0, 0, 0. Here it is 4. Would I lie to you? Is it 4? And here it is 4 as well, multiplied by this nice matrix. Let's finish it down. Wait, isn't it 0? Ah, come on.
Let's put it on the map.
No, it's not 1. It's not 1. It's my mistake. It's 0. This is the second one in the row, and it's the first in the column that they're not meeting. And now it is 0. So, proof by trying.
I love that.
Yes, I do love it as well. I should use it, outside the method as well. How do you know that? I said so. Okay, so that's our minimal polynomial. Okay, nicely done. If you have any questions, feel free to ask them. Next week, B'ezrat Hashem, we'll start the next subject, of course, using the minimal polynomial and the characteristic and the Kylie Hamilton. But the next important and less subject about matrices. Then week after next week, or probably even after Asara B'Tevet, we'll start the second part of the course, talking about what is called the inner product. But let's stay alive till the next subject. Huh?
There are two parts to this part.
Yes, linear algebra 2 and linear algebra 2, the multiplication strikes back or something like that. Yes. The night linear algebra 2, Night of the Dead, something like that. Minus and minus. Maybe